Hello everyone, I welcome you all to Physics Wala, and in this session we are going to discuss the next portion related to atomic structure, or I can say the chapter which is structure of atom. So basically in the previous part we were discussing about the basics related to the structure of atom. Now it's time to apply the entire conceptualization of the structure of atom to understand what is actually the atomic models. So basically in this particular session we are going to focus on three different models of a particular atom. First one is the Thomson atomic model. Then we are going to discuss about the next portion, which is Rutherford's nuclear model, and last part we are going to discuss about the Bohrs atomic model and what are the various concepts which are actually useful to determine these atomic models. Now basically if I talk about the revision part, whatever we have discussed in the previous two lectures, I can say that is the introduction about the atom. We started with the Dalton's atomic theory, then we discussed about the concept related to the structure of atom, or I can say the analysis part of structure of atom. Now in that case we started with the first part, which is Dalton's atomic theory, or I can say Dalton's theory. Then we discussed about the next concept, which is the discovery of fundamental particles. Then we discussed about the next part. After discussing about the discovery of electrons, protons as well as neutrons, we had some various concepts, which is cathode ray experiment, which is anode ray experiment, as well as the discovery of neutrons. Then we discussed about the basic idea about the atom. Now in that case, while we were discussing about the basic relations related to the atomic structure, we found out that in case of electrons, if I'm talking about the movement, it somewhat looks like a particular wave. Then we discussed about the characteristics of wave, and we started the discussion about electromagnetic radiations. After that particular part, we discussed about some conceptualization related to particle nature also, which is your photoelectric effect and black body radiations. And last part was Planck's quantum theory. I hope up to that part everything is clear to everyone. This was the basic discussion, whatever we have discussed till now. Now I gave you certain questions as your homework. If you can see the previous lecture, you can see there were two questions which I gave you as a homework. So let's try to discuss that particular part first. So the question says a bulb emits light of a wavelength 4500 angstrom. The bulb is rated as a 150 watt and 8% of the energy is emitted as light. How many photons are emitted by bulb per second? So basically in this case, I'm going to use the formula that total energy will be equal to NH nu, or I can say that will be equal to NHC upon lambda. Now for that particular part, we know that C has a specific value, which is a 3 multiplied by 10 raised to the power 8 meter per second. If I talk about the value of lambda, which is already given in this particular case, that is 4500 angstrom. So I can convert this particular part as 4500 multiplied by 10 raised to the power minus 10 meters, because 1 angstrom is equal to 10 raised to the power minus 10 meters. From that particular part, we can say that we have the value which is 45 multiplied by 10 raised to the power minus 8 meters. Okay, this part is sorted. Now if I talk about the value of H, we know that value will be 6.626 multiplied by 10 raised to the power minus 34 joule second. Now the entire portion is already clear to us. We need the value of E total, first part, and then the unknown portion in that case is total number of photons which are basically emitted in that particular case. Now we have the value that the bulb is rated as 150 watt. It means per second it's going to liberate 150 joules of energy. So I can say energy liberated or I can say not liberated, emitted by bulb per second will be 150 joules. Now from this particular part we can say that only 8% of the energy is emitted as light. So basically total energy emitted as light will be 8% of the entire value, which is 150 multiplied by 8 divided by 100. So we can solve this. That will be equals to 120 divided by 10, that will be 12 joules. So now we have the entire amount of energy, which is 12 joules. We know this particular part, which is going to be 12 joules, and we know h nu, or I can say hc upon lambda. I can simply place the value here. So after putting the entire values, we will left with 12 will be equal to n multiplied by 6.626 multiplied by 10 raised to the power minus 34 multiplied by 3 multiplied by 10 raised to the power 8, and the entire value is divided by 45 multiplied by 10 raised to the power minus 8. So from that part we can easily calculate the value of n. So I can say first of all this is going to be 3 4s are 12, I guess, yes. 45 is going to be 90, 180. So that will be n is equal to 180 multiplied by 10 raised to the power minus 8. Okay. Then the entire value is divided by 6.626 multiplied by 10 raised to the power minus 34. Now if I am moving this particular part here, that will be minus 8. So minus 8 will be minus 16. So that will be minus 16. Minus 16. Ten raised to the power minus 16, and 10 raised to the power 6.626 multiplied by 10 raised to the power minus 34. Okay, I hope this part is clear. Now we have entire values related to this particular part. We have to just solve this entire part. I am writing it here. So n value finally will be equal to 18 multiplied by 10 raised to the power minus 15 first part multiplied by 10 raised to the power 34 divided by 6.626. So that will be 18 divided by 6.626 multiplied by 10 raised to the power. So this is 34 and this is 15. So 15, 20, that will be 19. Okay, that will be 19. So you just have to solve this particular part and let me know the final answer. Okay. And I guess most of you already solved this particular question very easily. So it's a very simple question related to the energy of total energy emitted by the photon as well as the number of photons which are going to emit that amount of energy. I hope this entire part is clear. Very simple question. Now let's talk about another question. A certain dye absorbs 4700 angstrom and fluoresces at 5080 angstrom. These being wavelengths of maximum absorption that under given conditions 47% of the absorbed energy is emitted, and calculate the ratio of the number of quanta emitted to the number of quanta absorbed. So basically first part is energy absorbed, first part will be equal to n absorbed multiplied by hc upon lambda, which is lambda absorbed. Now energy emitted will be equal to n emitted multiplied by hc upon lambda emitted. Okay, so these are the two formulas which we are going to use in this particular case. Now the question says that under a given specific conditions 47% of the absorbed energy is emitted. So the energy emitted, we can say from this particular part that energy emitted will be only 47% of energy absorbed. So I can say this value, which is n emitted multiplied by hc upon lambda emitted, will be equal to 47 divided by 100 multiplied by n absorbed multiplied by hc upon lambda absorbed. Okay, so hc and hc are same, so you can cancel out this entire part. Now from this particular case, we can say certain dye absorbs at 4700. So lambda absorbed will be 4700 angstrom, and lambda emitted is basically equals to fluorescence at 5080 angstrom. Okay, so you can put the values here, and you have to calculate the ratio of the number of quanta emitted to the number of quanta absorbed. So n emitted divided by n absorbed will be equal to first part 47 divided by 100 multiplied by first part, which is n absorbed, divided by next part, which is, sorry, not n absorbed, that will be lambda emitted divided by lambda absorbed. I hope this part is clear. I hope this part is clear. I hope this part is clear. Okay, so we have put the values. I am just moving this n absorbed to the lower side, and I am moving this particular part to this side. So you can see this is the final equation. We know the lambda emitted and lambda absorbed. We can put the values and solve the entire equation. That will be 47 by 100 multiplied by, that will be 5080 divided by 4700. So you can say that will be 4710. So that will be 0.508. That will be the final ratio. I hope this entire part is clear. Very simple question. By simply putting the formulas, you will get the final answer. I hope this entire question is clear to everyone. Now it's time to talk about the next portion. After discovering the entire portion related to the discovery of fundamental particles, Thomson tried to actually explain the atomic model, and in that case the model is actually known as Thomson's atomic model. Now in that case, he simply said that atom is a positively charged uniform sphere in which electrons are embedded in between to maintain the electrical neutrality of the atom. So first point, Thomson talks about the electrical neutrality of the atom, how to maintain, because atoms are electrically neutral in nature. So how to balance this particular part? Let's assume that atom is spherical in nature. If the atom is spherical in nature, it means positive and negative charge are uniformly spread throughout, and in that case the negatively charged electrons are embedded inside the sea of positively charged protons. So that was the basic idea related to the model. Okay, so this is the first explanation about the Thomson's atomic model. Now in this case, you can see like the model is slightly lame, but at that time it was like a very fruitful result. They tried to explain the idea about the entire structure of atom, in which they considered that atom is definitely going to be spherical in nature. So in that case, we are talking about the uniform sphere formation. This is the first part. Now they simply compared the entire part with general life things, like they considered this particular part as a plum pudding model or a watermelon model. So in that case, different names like plum pudding, raisin pudding, or I can say watermelon model were actually the names which were given to this particular model. Because if you see a watermelon, you can see a positive part like the red color portion, the actual juicy portion, and there are certain seeds which are embedded inside that particular part. So these seeds are like the electrons which are going to maintain the electrical neutrality inside the sea of positively charged protons. Okay, so this was the basic idea, like plum pudding, raisin pudding model, or I can say the watermelon model. I hope this entire part is clear to everyone. Very basic analysis. Now if you compare the entire part, we are considering the atom is going to be sphere, and in that case of a sphere, we have positive charge uniformly spread and the electrons are embedded inside to maintain the electrical neutrality. So Thomson only focused on the electrical neutrality of the atom. Now in that case, like there were some discrepancies definitely, because the consideration is if the electrons and protons are uniformly spread, it means the entire mass of the entire atom is going to be uniformly spread. So from that particular part, you can say that mass, okay, it's already written that mass of the atom is assumed to be uniformly distributed over the atom. So this was the consideration But again, we know that there are some discrepancies, and the main discrepancy is after the discovery of this entire model, scientists actually were looking to the explanation of this particular part. So it was a simple explanation related to the structure of atom, but they were trying to prove that the actual structure of atom is exactly looking like this, because they already knew about the mass of electron, mass of proton, that was already known. So it means they have certain mass. If a particular atom consists of these electrons and protons, it means atom is heavy. Whatever mass is actually present inside the atom is just because of the presence of electrons and protons, and if they are uniformly distributed, it means the entire mass of the atom is going to be uniformly distributed. Now from that particular part, the main drawback of this experiment or this model was the experiment which was trying to prove the actual analysis of Thomson model, and that particular experiment is Rutherford's gold foil experiment. So basically, at that time, Rutherford was very obsessed with the radioactive elements, and he was studying about the radioactive elements, and the entire conceptualization of radioactive elements were already known at that time. And I told you, like, if we are considering the radioactive elements, if we are considering radioactive elements, in that case, the most important thing is you can see three different type of radiations emitted by the radioactive elements. In that case, first one is alpha rays or alpha particles. Next one was beta particles. And last part is gamma particles. These were basically positively charged, they were basically negatively charged, and they were neutral. Penetration power of alpha particles was very low. The beta particles have they had the moderate type of penetration power, but the penetration power of gamma particles or gamma rays were very high. Now in this case, you can see this alpha particle is nothing but the nucleus of helium, which is a 2He4. Okay, so this entire conceptualization was already established at that particular time. And if I talk about the beta particles, they are nothing but the electrons, and basically when the nucleus is not that stable and it's going to convert into protons and electrons, those electrons which are going to be emitted are basically your beta particles, and in the same way the gamma particles were actually totally neutral. That is basically the unstable nucleus. I hope the entire part is clear about the entire analysis of a Thomson model. And the Rutherford was working on the basic experiments related to alpha particles. Basically, these are positively charged helium nucleus. Now he thought, like, if let's say I'm taking a particular atom or atomic sheet which is very thin. Very thin means, let's say, it's approximately atomic level thin, and if I'm bombarding the entire part of that thin atomic sheet with these alpha particles, being positively charged particles, they are going to interact with the positive charge of the atom, and in that case you can see when same charges are going to strike together, definitely there will be a force of repulsion. And you can see when I'm bombarding the entire part and there is positive charge, this is also positive charge, then definitely it's going to show certain deflections. So he was trying to study that particular part, and that is nothing but the Rutherford's scattering experiment. Now in this particular experiment, what he did, the observations were very easy. Okay, before observations, the entire setup you need to understand. First one, we have a source of alpha particles. So he took a radioactive element or a radioactive source which is capable of generating alpha particles. So this was the source of alpha particles. First one was the source of alpha particles. From that you can see alpha particles are actually ejecting, or they are actually going towards the sheet, which is the atomic thin sheet. Now in that case you can see there is a small hole, so that their path is going to be a straight line. They are not going to deviate from their path. Now from that particular part, he covered the entire part with another protector, I can say, and in this case this protector contains ZNS, which I already told you in the cathode ray experiment. So since this ZNS is basically showing the effect of scintillation, you can see some spark is going to produce when these alpha particles, because they are charged particles, when they are going to strike on the surface, you can see a sparkling. Now this sheet was considered to be gold foil, which is of atomic thin level. Means he generated or he created a atomic thin sheet or thin foil of gold. Basically, why he chose gold? Because in case of gold, you can see the gold has an excellent ductile nature. It means you can convert the entire part into atomic thin sheet. Now it's not like one atom is present inside the sheet. It means it is approximately, I can say, 0.0004 centimeter, which is approximately 2000 atomic thin sheet. So yeah, it was commendable job. So he chose the gold foil. Now it was time to start the experiment. So the entire setup was ready, everything was ready, and he was also ready. He was thinking like, if these positively charged particles are going to bombard on the atomic thin gold foil, definitely he's going to expect some deviations. But when the experiment started, most of the deviations, as you can see, like these particles are showing the deviations, you can see most of the particles were showing the scintillation on this point only. It means there is no deviation in this particular case, no deviation in this particular case. Now this entire part was rotating, so to check the entire portion related to the scintillation part. So when I'm moving this entire source part to different directions, I can see like it's going to hit different portions of the atomic thin sheet. But in most of the time, there were no deflections in the entire portion. After some experimentations, after some bombardment, he found out that there are slight deviations in the path. There are slight deviations in the path. There are slight deviations in the path. And then he tried to do the same experiment. He found out like there are certain portions where he was able to see certain deflections when this atomic thin gold foil was bombarded with the alpha particles. But these deviations were not that significant. After that, one more scientist actually was working on this particular part. Basically, Rutherford and his junior researcher was working on this particular experiment. And one more scientist, I actually didn't recognize the name in this moment, but yeah, there was one more scientist who was working on this experiment. And then he found out that after certain experimentations, after 20,000, approximately 20,000 bombardment, you can see some of the rays, when they are hitting at a particular point, they are moving, or they are actually tracing their trajectory. They are moving in the same direction, they are coming back in the same direction at the angle of 180 degree. So this angle of deviation was a theta. Okay, generally in most of the cases, this theta was approximately equals to 1 degree or less. It means there is no deviation. In certain cases, this theta was approximately 50 degree or 60 degree. In one of the case, after 20,000 bombardment, there was one case where the theta was exactly 180 degree, and he was really confused. He was expecting something else, because the positive charge is uniformly distributed. If the positive charge is uniformly distributed, every time I'm going to see certain type of deviations, because positive charge is distributed and I'm bombarding the entire part with the positive charge. So I need to show that this Thomson model is going to be correct. But these results were entirely different. They were showing something else, that there is a particular point when the alpha particles are going to bombard at that particular point, then they are going to come back exactly same at 180 degree. So it means, let's say if I'm talking about the atom, let's say this is the atom, different atoms are present. Now in this case, you can see if the alpha particle is moving in this direction, you can see there is no deflection. Or I'll try to explain with only one atom. I'll try to explain the entire part with only one atom, so that this entire part will be clear to everyone. So let's say this is the structure of atom. Okay, and in that case, he was trying to see the deviations. In first case, in most of the cases, the deviations were like this. They were moving like this, that something is not present. If something is vacant, if something is hollow, then only you can see a straight line path after the bombardment. There is no deflection. But in certain cases, he found out in most of the cases these deviations were not there, not at all there. These deviations were not there. But in certain cases he found out, that there are some slight deviation, not that prominent one, but there were some slight deviations in their path. There were some slight deviations in their path. Okay, he saw like this, there is some deviation in their particular path, and there was one point where he found out that something is actually present at a concentrated point. And when I'm using this particular bombardment to this direction, okay, when I'm bombarding the entire part to this direction, I can see it's going to trace back its path. Other than that, the radiations were like moving in different type of directions. They were moving in different directions. So this is the most important observation. You can see if it is not exactly directed towards this particular point, you can see slight deviations when it is close. When it is far from this particular point, you can see these were undeviated. This was the actual observation by Rutherford. So he simply said that I am not talking about the entire structure of atom, but there is one point, there is one concentrated point where the entire mass of the atom is actually concentrated at that particular part, and he named that particular part as the nucleus. That's why we know that the Rutherford model is not the actual atomic model, but it's the nuclear model of atom, because Rutherford actually focused on this one particular part, that we have to find out where is the location of electrons as well as where is the location of protons. So this was the entire experimentation done by Rutherford. Now if I talk about the points, observations were very clear that most of the alpha particles passes straight through the gold foil without any deviation. It means the entire part is hollow. We can say most of the portion is empty. From this part we can say if the deviations are actually straight, there is no deviation, it means the most of the portion inside the atom is empty. Now small fraction of particles deviated through a small angle, which shows something is present. Something is present at the center. Okay, now very few particles bounces back. It means one in approximately 20,000 particles had the angle of deviation which is 180 degree. It means the entire mass of the atom is not uniformly distributed, but it is actually concentrated at a single point. It means that the entire mass is concentrated at a single point. Okay, this is the entire part related to the observations of Rutherford's nuclear model or Rutherford's gold foil experiment. I hope the first part is clear. I hope the entire setup as well as the observation part is clear to everyone. This is the basic portion which you need to understand. Now it's time for the conclusion. So conclusion is very easy, that we can say from this particular part, we can simply say that most of the space inside the atom is empty, which was not in accordance with the Thomson's atomic model, because Thomson said that atom is spherical in nature and the entire mass is uniformly distributed. But this experiment found out that entire mass is actually not uniformly distributed. Most of the space is actually empty. Now the next part is positive charge is not uniformly distributed in the atom. It is concentrated and occupies a very small space inside the atom. And this term was nothing but nucleus, the point where the entire mass was concentrated and the positive charge was concentrated is basically your nucleus. Because when alpha particles which are already positively charged are present, when they are going to bombard or they are going to subject it to a particular point, definitely in that case you can see there is a deflection, because positive charge is going to repel each other. So that was the observation related to the Rutherford's entire experiment. Now mass of the atom is present in the small volume and is located at the center of the atom, and this part is termed as your nucleus. I hope this part is clear. And alpha particles going straight to the nucleus suffers maximum repulsion because the entire positive part is concentrated at that point. So definitely there is maximum repulsion in that particular case. I hope this entire portion is clear to everyone. Very simple explanation related to the Rutherford's gold foil experiment. Now, that was the time when Rutherford decided to give its nuclear model after this experimental results. So, he simply said that atom consists of two parts. First part is the nuclear part and next part is the extra nuclear part. So, in the nuclear part, you can see the entire part of the nuclear portion is present at the center of the atom, and there is extra nuclear part also present around the nucleus. Now all the protons are positively charged is concentrated at this center of the atom, which is the nucleus, and electrons are actually present in the extra nuclear part and they revolve around the nucleus. So these were the two basic analysis related to the Rutherford's atomic model, or I can say nuclear model. I hope up to that particular part everything is clear to everyone. Just look at these observations, whatever we have discussed till now. It's a very simple thing. First he decided to do an experiment, which is the gold foil experiment. After the observations, he decided to give its theory, which is nothing but Rutherford's nuclear model of atom. Okay, now the next part, in that case you can see this is the representation. So again in this case atom is considered as a spherical part in which the nucleus is present at the center and electrons are revolving around the nucleus in the extra nuclear part. So this particular portion is the extra nuclear part where electrons are present, and this particular part is already the nucleus where the entire positive charge is concentrated, as well as the mass of the entire atom is concentrated at this particular point, because the mass of electron is very less in comparison to the protons. You know, the mass of proton is approximately 1837 times more in comparison to electrons. So definitely, if all the protons are concentrated at a particular point, it means the entire mass is concentrated at a single point, and that's why most of the region is empty. So you can see no deviation, but the alpha particles which are close to this positive charge, they can feel the positive field, I can say, so they can be repelled by that particular part. But when there is actual bombardment directly to this nucleus, you can see 180-degree deviation in that particular case. So that was the entire idea related to the Rutherford's nuclear model. Now the next thing which he tried to explain, that the volume occupied by the nucleus is negligibly small as compared to the total volume of the atom, and he simply said that there is a specific relation. If I talk about the entire volume of the atom, I can say that actually depends upon the mass number, because the entire part was working around mass. So we can say the entire portion is approximately directly proportional to the mass. As the mass of the atom is going to increase, definitely in that case its volume is going to go up. That was the basic idea related to the particular model. From this particular part, you know, we are considering atom as a sphere, so definitely that will be 4 upon 3 pi r cube. So from that particular part, you can say that r cube in that case is directly proportional to mass number, and r will be directly proportional to a raised to the power 1 by 3. That was the basic analysis related to Rutherford's nuclear model. And he simply said, when I am comparing the size, when I am comparing the radius of the nucleus with respect to the radius of atom, there is a large difference. Let's say the radius of the nucleus is r0, let's say, which is very small. So the radius of the atom is going to be 10 raised to the power 4 times, approximately more than the value of the radius of nucleus. It means nucleus is very small in size. Okay, so that was the basic idea related to the entire portion. So you can say that was the equation I was talking about, that the radius of the atom depends upon the mass number and raised to the power 1 by 3. So basically this r0 is a constant term with respect to different type of atoms, we can say, because it's a proportionality constant. You know that equation comes out as r is directly proportional to a raised to the power 1 by 3. When I am removing this particular part, this becomes r0 a raised to the power 1 by 3. So this particular part is a proportionality constant as a specific value. Okay, I hope this entire part is clear to everyone. Now from that particular part, you can say the volume of the nucleus is about 10 raised to the power minus 42 meter cube. If I am comparing, the atom has a volume which is 10 raised to the power minus 27 meter cube. It means the volume of a nucleus is a 10 raised to the power 15 times than that of that particular atom, which is very, very, very small. So if I talk about the radius, always remember, let's say the radius of atom is, let's say, how can we say, let's say this particular part is r, okay, and radius of nucleus is, let's say, r1, let's say. So always remember that this r1 is approximately 10 raised to the power 4 times smaller than atom. Okay, approximately 10 raised to the power 4 times is smaller than atom. I hope this entire part is clear to everyone. This is the basic explanation which was given or which was compared by Rutherford to explain the size of nucleus as well as the size of entire atom. Okay, now if I talk about the next particular part, although you may not find this part very frequently, but there were certain questions in JEE as well as JEE Advanced as well as some other examinations. I am including everything. So it may be asked that somebody is talking about the distance of closest approach. So you should know this part is not entirely present in NCERT, but yeah, this is the thing which you should know. So what is the meaning of this distance of closest approach? It means when the alpha particles approaches the nucleus to make a head-on collision. Means let's say I am moving the alpha particle in this direction, let's say, and this is the nucleus which is present, and this nucleus is positively charged. These alpha particles, whatever I am using, they are also positively charged. It means they are not going to collide exactly. They are going to move towards that particular part, and you can see it has a positive force of attraction. It has a region where you can experience the force of attraction, the positive force of attraction. So this positive part is not going to directly combine with this positive charge. Simple experiment, when you are trying to attract two magnets having same pole, north pole with north pole, south pole with south pole, you can see there is a minimum distance where you can push these two together and they can be really balanced. After that you have to put an extra effort to combine them because they are not going to attract towards each other because of the same type of poles. Just like that, they are going to move towards each other and they will try to settle down at a specific distance, which is basically the distance of closest approach, where the entire force of attraction and force of repulsion are actually balanced. So let's say this alpha particle moves to this particular point only. Now the distance between these two parts is basically the distance of closest approach, and this is the distance where this alpha particle can move up to this particular point. It can move, it will not collide directly to the nucleus because it has a specific force of attraction, it has a specific region of positive charge, and again I'm bombarding positive charge particles, so they can move to a particular distance where the entire forces are going to be balanced with each other. Now in this particular case, you can say that the alpha particle approaches to the nucleus until Coulombic potential energy, until its potential energy of repulsion becomes equal to the kinetic energy. So that was the point. So what you have to do, you just have to compare their kinetic energy as well as their potential energy. So this is the point where kinetic energy by which that alpha particle started will be balanced by the potential energy. Okay. Now if I talk about the formulation, you know, kinetic energy is half mv square that will be equal to potential energy, which is k multiplied by z1 z2. Z1 is the charge of this particular part, Z2 is the charge of that nucleus. I can take any part. So in this case we have, let's say, Ze charge. Z is the atomic number and E is the charge of that particular nucleus. So you can say in this particular case alpha particles are basically 2He4. So in that case Z value is 2 and charge is again E, so that Ze will be equal to 2E in this particular case. E is basically 1.6 multiplied by 10 raised to the power minus 19. So we know all these things. So if I am comparing this entire part, these are going to be balanced with each other. Now in that case, I can say this R value will be equal to K Z1 Z2 E square upon half mv square. Now that R is basically distance of closest approach. This particular part is known as distance of closest approach. Now the nucleus must be further smaller than the distance of closest approach. Definitely nucleus must be smaller. If the like if this particular part is smaller than the nucleus size, it means the alpha particle whatever I am bombarding is actually more closer towards the nucleus, which is not possible. So I can say this approach is absolutely correct. So you just have to put each and every value in this particular case to get the final answer. Okay. Now, the drawbacks of Rutherford model was very easy to understand. Basically, the Rutherford was talking about a basic analysis, that there is a small part inside the atom, which is your nuclear part. Now, in this nuclear part, entire positive charge is concentrated and the electrons are present in the extra nuclear part and they are rotating. They are moving in the direction. Okay. Now, from this particular part, the main explanation is when a charged particle is going to move, when the charged particle is rotating. He was simply saying that whatever rotation is happening, it means there is some centrifugal force which is actually balanced by the positive force of attraction between the electrons and neutrons, sorry, electrons and protons. So it means he simply said when the electron is rotating, when the electron is rotating, it means the centrifugal force is actually balanced by the electrostatic force of attraction. Clear? Okay. Okay. It means electron is rotating in the extra nuclear part. But the main thing is when a charged particle is going to rotate, main thing is when charged particle is rotating, it's a very simple phenomena. When a charged particle is rotating, definitely it's going to release certain amount of energy. Energy is going to liberate. If the energy is liberating, it means every time when it is rotating, it is losing some amount of energy and it is coming closer towards the nucleus. It is coming closer towards the nucleus, and there will be a one time when the entire part of the electron is going to be combined with the proton, and that arises the question on the stability of the atom. So basically this model was not able to explain the stability of the atom. So that was the most important I can say limitation related to the Rutherford's nuclear model. Other than that, there were some also discrepancies. It was unable to explain the arrangement of electrons in extra nuclear part. He was unable to explain the line spectrum. He was unable to explain line spectrum. Okay, so these were some limitations, I can say drawbacks related to Rutherford's model. I hope this entire part is clear. Just have a look at it and then we will start with the next model. Okay. This model could not explain the distribution of electrons present in the extranuclear part, we know. This model could not explain the line spectra of the atom. That part we already know. I'll try to explain the line spectrum after completing the Bohrs atomic model, because that will be much more efficient way to explain the line spectrum. Okay. Now, there is a question: with what velocity should an alpha particle travel towards the nucleus of a copper atom so as to arrive at a distance of 10 raised to the power minus 13 meter? It means in this particular part, this is the distance of closest approach. Okay, this is the distance of closest approach. So we have this particular part. We know that at this particular portion, half mv square will be equal to k z1 z2 e square upon r. That part we have already discussed in the equation itself. You can see the equation. This is the equation related to the entire part. So we have already established the relationship. Now in this particular case, I'm just giving you the values. You just have to solve this question by yourself and let me know the final answer. Okay. Now in this case, we have to calculate the v square. So v square will be equal to 2k z1 z2 e square upon r multiplied by m. Okay. Now in this case, this is the mass of alpha particle. This is for alpha particle. Okay. So in this case, I can say that we have alpha particle. This is the alpha particle. And this is your nucleus of copper. It means Z is equal to 29 in this particular case. Z is equal to 2 in this particular case. So we have the value of Z1, we have the value of Z2. Just put the values. V will be equal to square root of 2k Z1 Z2 e square upon r into mass of alpha particle. Okay. So just put the values and you will get the answer, final answer. I hope this entire part is clear. I hope this entire part is clear. Very simple question. So this will be your homework. If you find any difficulty while solving this question, just let me know in the comment box. I'll help you and I'll discuss that particular part in the next session. Okay. Just try to put the values and let me know the final answer. Okay. I'll give you the answer in the next class also so that you can cross verify. Okay, now the next part was Bohrs atomic model. Now this was the advanced version of the model at that particular time, because he saw the experimentations related to Thomson model, although there were no such experimentation at that time, and he entirely studied the part of Rutherford's nuclear model. So he thought we can make few changes in the Rutherford's model and everything is good to go. So he said that this model was based on the quantum theory of the radiation and classical law of physics. So he tried to combine Planck's quantum theory as well as he tried to combine all the classical laws of physics into his model. And it gave new idea of atomic structure in order to explain the stability of the atom and emission of sharp spectral lines, because he was working on the limitation parts of Rutherford model, and one of the limitation was he was unable to explain the first part, that what is the location of electrons, where the electrons are actually present inside the atom, and how can you explain the line spectrum. Line spectrum means whenever a particular atom is subjected to a specific light, you can see a sharp lines are going to emerge at a specific wavelength. So that particular model was unable to explain this entire part. So he was working on the entire explanation, and he thought that we can combine Planck's quantum theory as well as classical laws of physics so that we can get a better idea about the atomic structure. Now in that case, he simply said the same postulates, that we have the nuclear part as well as extra nuclear part. In the nuclear part, you can see atoms nucleus is present, which is a very small portion, and the entire mass is actually concentrated at that particular point, which is the nucleus, and this is again positively charged. Okay. Now the extra nuclear part is basically where the electrons are present. So this is for the negatively charged part. Now he simply said that electrons are present in the extra nuclear portion and they revolve around the nucleus in circular orbits or shells. So this was the first time when somebody actually defined the path of the electrons. He simply said that if I am talking about the extra nuclear part, the electrons are revolving around the nucleus, that is for sure true, but they are revolving around the nucleus in the circular fixed path. So this is the circular fixed path. This is the fixed path having fixed energy. If the energy is fixed, if the energy of that path is fixed, So when the electron is present in that particular path, it's not going to lose its energy. So that was the first time when somebody uses a term which is basically orbit, or I can say shell, having a fixed path as well as fixed energy. I hope this part is clear to everyone, and this is the important portion. This is a very important portion. Okay, now if I talk about the analysis of these fixed or stationary paths, we can say circular paths having fixed value of energy associated with them are actually your orbits, or I can say shells. Okay, so when I'm using the term shells, I can say we have K shell, we have L shell, we have M shell, as well as we have N shell. And when I'm using the term orbit, I can say we have a first orbit, we have a second orbit, we have a third orbit, we have fourth orbit. So first orbit means we are talking about the K shell. Second orbit we are talking about the L shell. Third orbit we are talking about the M shell. Fourth orbit we are talking about the N shell. It means he correlates the entire part with principal quantum number. Definitely that part we are going to discuss in the quantum mechanical model, but he fixed the entire part with the principal quantum number, which is shown by n. Okay, so every type of atom contains at least a finite value of n. So n can be 1, 2, 3, 4 and so on. Okay, so this was the basic idea related to the stationary orbits. I hope this portion is clear to everyone. Now, the energy of each stationary orbit is fixed, already fixed, and along with the increase in the distance from the nucleus, the value of energy also increases. Now, this is the most important portion you have to understand. When the electron is present closest to the nucleus, it means in that case the force of attraction between the electron as well as nucleus is more. When the electron is moving far from the nucleus, it means this force of attraction is going to decrease. In that case, you can see when the electron is closest to the nucleus, it is highly stable. When the electron is far from the nucleus, it is not that stable and it can easily be loose. So you can say that when the we are talking about the distance, the energy is distance dependent. The distance is increasing, it means the energy of the electron is going to increase. Always remember, for first orbit, energy is minimum. Minimum means we are talking about a negative term. Negative value is also present. Okay, and when electron is present at an infinite distance, for electron at infinite distance from nucleus, it means in that case its energy will become actually 0, because there will be no force of attraction experienced by the electron from the nucleus. So you can say the energy is increasing in terms of negative part. Initially it is for hydrogen atom, if I talk about this particular part, it is approximately 13.2, minus 13.2, then it's going to be minus 6, then it's going to be minus 1.41, then it's going to be approximately equals to 0. So you can see energy is increasing. Least negative term is basically corresponds to the maximum stability of the atom. So that particular part you have to understand. Most of the students are actually confused in this particular part. What is happening? So if the electron is present in this particular portion, it is highly stable. In this portion, less stable. In this portion, some less stable. If it is at infinite distance, it means there is no force of attraction between the nucleus and the electron. It means its energy is going to be maximum, and this arbitrary value we always chose as 0. So 0 is the maximum energy, I can say. So when the electron is coming closer, you can see the negative amount is going to increase. I hope this entire part is clear to everyone. This is the most important observation related to Bohrs atomic model. Now one thing which I want to explain, just wait for a second. Just note one point, that this model was only applicable for one electron species. That was the limitation. Not the limitation, but yeah, first of all, you just like your gaseous state, you first have to idealize something. You have to understand the ideal gas equation so that you can correlate the entire part with the real gas equation. So just like that, this model was the conceptualization to understand a hypothetical model in which only one electron is actually present. So this particular model is able to explain hydrogen, He positive, Li2 positive, Be3 positive, and so on, because every species only contains one electron. So that you can see, you can only work on one factor, the force of attraction between the electron as well as nucleus. That's the only thing. So this is the ideal model, I can say. And after that, we have the most advanced version, which is the quantum mechanical model, because it considered each and every part. Although again, in quantum mechanical model, there are certain assumptions also to simplify that particular model up to your level. But yeah, this is the idealized model where we are only talking about the one electron species. So always remember, whenever we talk about Bohr atomic model, this atomic model is applicable in case of one electron species only. I hope this entire part is clear to everyone. But this model was able to explain the entire portion related to one electron system. He was able to talk about the velocity of the moving electron in the circular path. He was able to talk about the distance from the nucleus. He was able to talk about the radius of the orbit. He was able to talk about the energy of the orbit in which electron is actually present. So you can see now it's the time to understand the basic relationship of the spectral lines, why the spectral lines were emerging in case of all the models, and Rutherford model was not able to explain because he was unable to explain the actual idea. He was unable to explain the actual idea about the arrangement of the electrons, but Bohr simply said that we are talking about the orbits. And always remember, if we are talking about the orbits, you have to understand that okay, so I'll try to explain the actual structure. Okay, correct है. Okay, I guess. Okay. Okay. You must be wondering like why I am creating something like this. So I'm explaining like this is your nucleus. This is your nucleus. Okay. Now you can see the first orbit is looking like this. Second is looking like this. Third is looking like this. Fourth is looking like this. Fifth is looking like this. And sixth is looking like this. It means as you are moving from the nucleus, away from the nucleus, you can see that this gap is more, this gap is more, this gap is more. Again, this gap is going to be small, this gap is going to be small, next gap is going to be very, very small. It means when the value of n increases, it means the energy is going to also increase, but the difference between the energy is going to decrease. So that you can see a actual visualization. This is not the actual visualization, but this is the actual visualization of the structure. So you must be very careful when you are dealing with this particular part. You cannot make every time same gap between two orbits. The gap is also going to decrease when the value of n is going to increase. I hope this part is clear. This is the representation I want to show. Now from this particular part, if I'm talking about the cross sectional view, you can see the cross sectional view here. Now you know that this point we can take this particular part with this color. Okay, okay. Now I'll try to explain that this is, let's say, this is n is equal to 1. Let's say this is n is equal to 1. This point corresponds to n is equal to 2. Okay. This point corresponds to n is equal to 3. This point corresponds to n is equal to 4. This point corresponds to n is equal to 5. Okay, this is the thing which I am trying to explain. Now in this particular case, what happens? Electron can be present in n is equal to 1. Okay, and when you are subjecting some amount of energy, when you are giving some amount of energy to this electron, it can actually absorb some amount of energy. It means now the energy of that electron is going to increase. Now he is able to actually jump to the next point. So definitely he is going to jump to the next available orbit. So from this n is equal to 1, which is the K shell, when we are giving some amount of energy to the electron, definitely this energy electron is going to absorb, and this energy we are talking about the Planck's quantum theory, because energy is discrete. So I can provide the energy in the discrete manner. So I'm using the energy term which is equal to h nu. So this is going to absorb some amount of energy. Now this energy, electron is present here, electron is present here, and there is some gap. There is some gap between these two parts, and this gap has a certain energy. This is the energy gap. This is the energy gap. Now let's say I am providing certain amount of energy to this electron. I am providing certain amount of energy to this electron. Now this energy is actually sufficient to cross that barrier, because this barrier has a some specific amount of energy, and I am providing the exact amount of energy. So the electron is going to actually absorb the entire amount of energy, and it will jump to the next higher orbit. And in this case, let's say this is the ground state. Let's say this is the ground state. This is the ground state. After absorbing the energy, electron can move to the excited state. Electron can move to the excited state. Now it depends upon the energy I am providing. I can provide the energy which is equals to this energy gap. I can provide the energy to this E dash gap. If I am providing the energy, electron will directly jump from this particular part to this particular part. I can provide the energy up to this particular gap, so electron can actually absorb the energy to jump from this particular point to that particular point. Okay, it's like a jump when Krish is jumping from building to building. It's a very simple example, because it has that specific amount of energy so that it can easily jump. So if I'm providing any amount of energy, it means I'm interacting the atom with light, because light has a specific amount of energy, or light of specific wavelength I can say. And if that energy matches with the gap between the orbits, definitely electron is going to absorb that energy, and it will go to the, or it will jump to the excited state. But it cannot spend the entire time at excited state, because in excited state the energy of electron is very high. It will again try to release the energy. So what happens then, this electron is eventually try to release the energy to come back to its ground position, and there is some loss of energy. It is the absorption of energy, first part, then it's the emission of energy. And this emission belongs to a specific wavelength region or a specific frequency region, so that you can see some sharp spectral lines which corresponds that electron transition is happening. So the spectral lines are basically nothing but a simple phenomena that different energy orbits are present, and electron is jumping from one part to another part, and after losing the energy, it will come back to its ground state by the loss of energy. That loss of energy corresponds to a specific wavelength which shows the spectral line. So electron can jump to higher orbit from any of the lower orbit by absorbing suitable amount of energy. That is the most important part, by absorbing suitable amount of energy. And electron can return back to any of the lower state from the higher state by the release of energy. So basically there are two phenomena which are occurring: absorption of energy and emission of energy. And in both the cases you can see some sharp spectral lines are coming, because that corresponds to the wavelength, or I can say frequency, where the electron is releasing itself, or where it is coming from higher state to lower state. That corresponds to the your spectral line. So you can see electrons excited by absorbing energy. So this is the energy absorbed, first part, energy absorption at different scales, and this is the part of electron emission. The energy is going to be released by the electrons to come back to its ground state. I hope this entire portion is clear to everyone. Very simple analysis and very simple clarification about the spectral lines origin. Okay. Now in that case, the next part was, because he was using the Planck's quantum theory, it means the energy of the orbit is not random. These orbits are highly fixed in nature. That's why I told you this gap is going to decrease after some time. The gap between the orbits is going to decrease after some time, because everything is not random, everything is highly specific. And he simply said that electron will only revolve in those circular paths where the angular momentum of that moving electron is integral multiple of h upon 2 pi. So if I talk about the angular momentum, we know that MEVR will be equal to NH upon 2 pi. So MVR is the angular momentum. For mass, we are using ME, mass of electron. V is the velocity by which electron is revolving. R is the distance, or I can say the radius of the orbit in which electron is revolving. So that will be equal to NH over 2 pi, because this was the mixture of your quantum theory, Planck's quantum theory, as well as your classical laws of physics. So definitely we have to use the quantization, because everything is specific. In case of orbits, nothing is based on the assumptions. He simply said that they have a stationary path. It means that in that case, electron cannot move anywhere inside the nucleus, anywhere inside the atom. It has to like maintain the dignity of the orbit, and it has to follow a specific path, and in that case its angular momentum will always be an integral multiple of h upon 2 pi. Okay, I hope this part is clear. This is the first portion. So you can say MVR is equal to NH over 2 pi. N value can be 1 2 3 4 5, because at least we need one value, like first orbit we need, and so that N actually corresponds to your principal quantum number. This is your principal quantum number. Okay, m is basically the mass of electron, v is the velocity of electron, r is the radius of electron, h is the Planck constant, which has a specific value. It means you can talk about the velocity of electron, you can talk about the radius of the orbit very easily. That's why this particular model gave the entire idea related to these basic properties related to electron. Okay, now it's time to talk about the radius of orbit, how you can calculate the radius of orbit. So first part is, if I'm talking about a specific distance at which electron is present, in that case you know that electron is revolving around the circular path. It is revolving around the nucleus in a circular path. It means whatever in the circular path, whatever centrifugal force is happening, that is actually balanced by the positive force of attraction, the electrostatic force of attraction between the nucleus and electron. So this is the electrostatic force of attraction, which is K Q1 Q2 upon R square, where K is already constant and has the value which is 1 upon 4 pi epsilon. So that has a specific value which is 1 upon 4 pi epsilon naught. Okay, now Q1 Q2 are the magnitude of charges whatever we are considering. First one is the nuclear charge and next one is the charge of the electron. R is the distance which is separating them. Now in this case, the centrifugal force is basically mv square over r. So we can say at the balance position, when the electron is revolving in a specific path, these two forces are going to be balanced. So we can say from this particular part that if I talk about the electrostatic force of attraction K Q1 Q2. So let's say I'm talking about this particular part. This is the nucleus having atomic number Z, and in that case charge is going to be Ze definitely. This is the electron, so definitely its charge is going to be E only. So this is the first and second part you have to understand. So I can put the value in the electrostatic force of attraction, that will be K Ze multiplied by E over R square. So that will be K Ze square over R square. Okay, this is the first part. This is not the capital K, this is going to be definitely small k. Okay, now next part, if you are comparing the entire part with mv square over r, which is the centrifugal force balanced by K Ze square over R square. So this is the first equation. Now we know that we have the quantization of angular momentum, which is mvr is equal to nh over 2 pi. So I can put the value of v, which is nh over 2 pi mr. So I can put the value here. I can put the value here. If I'm putting the value, we have m by r multiplied by v square. V square will be n square h square upon 4 pi square m square r square will be equal to 𝐂𝐍𝐸 square over r square. So this r square is going to be cancelled out with this particular part, m is going to be cancelled out with this particular part, and I guess you will left with r on that side. R will be equal to n square h square, okay, upon 4 pi square m 𝐂𝐍𝐸 square. That will be the final value. You can see that I just have correlated the entire part. R square h square cancel, r is going to move on this side, this entire part will come down, so that will be n square h square upon 4 pi square m 𝐂𝐍𝐸 square. Okay, I hope this part is clear. I hope this part is clear. So finally you can see this equation. You can see this equation. Now from this particular part we know that r will be equal to we have h square having specific value divided by 4 pi square specific value, mass of electron is having specific value, k is having specific value, e square is having specific value, and we have n square by z. These are the two variables, but otherwise you can see the entire part, this entire portion will be a constant. This particular part will be a constant. And you know, after solving the entire part, you will left with the equation which is r is equal to 0.529 n square upon z in terms of angstrom. In terms of angstrom. Okay. Now in this particular case, you can see for hydrogen atom, this n value is 1 because 1 electron is present, so definitely it should be in first orbit. Z value is also 1. For hydrogen, the atomic number is also 1. So you can say in case of hydrogen atom, the R value will be 0.529 angstrom. I hope this entire part is clear to everyone. Very simple explanation, very simple explanation. So for hydrogen atom, you can say if the electron is present in the first orbit, then definitely it is 1. If it is present in the second orbit, then definitely it will be 0.529 multiplied by n square, which is 4. For third orbit, it will be 3 square, which is 9. So you can say that will be the value in angstrom only. In picometer, that will be 52.9 picometer, or in nanometer, that will be 0.0529 nanometer. I hope this entire portion is clear. But again, we were talking about the hydrogen-like species. So you know that the Rn value is basically a specific value which is R naught multiplied by n square by z. So always remember, this is the most important formula which we are going to use. This R naught is a constant term, and for H atom generally this value is equal to 0.529 angstrom. I hope this part is clear. So you just have to use this particular formula. Okay, so we have one question. Calculate the ratio of radius of third Bohr orbit of beryllium 3 positive ion and fifth Bohr orbit of lithium 2 positive ion. Okay, so we know that Rn is equal to R naught multiplied by n square by z. Okay, now first part. For beryllium 3 positive ion, hydrogen like species, beryllium 3 positive, definitely. So in this case, Z value will be 4. Hydrogen, helium, lithium and beryllium. So Z is 4 and N value is already given, which is third Bohr orbit. So this is third Bohr orbit. Okay. Next part, we have for lithium 2 positive ion. Again, lithium 2 positive is hydrogen like species. It means its Z value is 3 and N in this case is fifth Bohr orbit is already given. So in this case, we are talking about the R of beryllium 3 positive, and it is the I guess third Bohr orbit, R3. R3 will be equal to R naught having specific value multiplied by n square, which is 9, divided by z, which is 4. So this is the first value. For this case, we can say R of lithium 2 positive, which is for the fifth orbit, that will be R naught, n square will be 25 divided by Z, which is 3 in this case. Okay. So we have to calculate the ratio of the beryllium to, okay. So ratio of beryllium 3 positives, third orbit radius, and radius of lithium 2 positives, fifth orbit, will be equal to, first part is R naught multiplied by 9 by 4 multiplied by 3 divided by R naught multiplied by 25. So I guess that will be, R naught is going to cancel out with this R naught, that will be 27 by 100. Okay, that will be 27 by 100, or I can say that will be 0.27. I hope this part is clear. Very simple question, very simple question. Okay, so that's how you can deal with these type of questions. Okay, and you can practice some more questions from NCERT itself, because you can find certain questions in NCERT. This is the basic portion. I'm not talking about the advanced portion. Definitely we are going to discuss some other questions related to mains as well as advanced level as well as NEET questions, but this is the basic part. First of all, you have to understand the entire conceptualization. Okay. Okay, now we know from the quantization of angular momentum, we have is mvr is equal to nh over 2 pi. So v in that case will be nh upon 2 pi mr. Now we know the value of r. So r will be n square h square upon 4 pi square mze square multiplied by k. That is the value of r. Can I put the entire value here? Yeah, definitely. So from that particular part, I can say that v velocity will be nh upon 2 pi as it is. Then we have a mass multiplied by r. R will be n square h square multiplied by, we have 4 pi square m k ze square. Okay, so this nh is going to cancel out this n as well as h. Okay, so this 2 is going to cancel out this 2, this pi is going to cancel out this pi square, m is going to cancel out this part, and we will left with velocity is equal to 2 pi k ze square upon nh. You will left with this particular part, 2 pi k ze upon nh. Okay, so you can see the value, that will be 2 pi ze square k upon nh. Ze square upon, yeah, exactly this is the value. Now from this particular part, you can say that 2 pi is constant. From this part, you can say that 2 pi is constant, e square is constant, upon h is constant. This is the entire part which is constant. This is the entire part which is constant. Okay, so the value of k can be determined with the help of epsilon naught, but generally that will be 9 multiplied by 10 to the power 9. Now in this particular case, you can see we will left with only one part which is variable, that is z upon n, that is variable. So after solving the entire constant part, you know, this is the v naught value, I can say. So the equation becomes v is equal to v naught z by n. Okay, so this v naught is having the value which is 2.18 multiplied by 10 raised to the power 8 centimeter per second. Okay, so you will be finally getting the value as 2.18 multiplied by 10 raised to the power 8 z by n centimeter per second. That is the value related to the velocity of electron moving in a specific orbit. Now for hydrogen atom, again you can calculate this entire part by putting the value 1, 2, 3 in different orbits. Now let's talk about a question. Calculate velocity of electron in third Bohr orbit of lithium 2 positive ion. Now in this particular case, that we know for lithium 2 positive ion, first thing which we know that its z value is 3, and next part which is required, that is n. N is third Bohr orbit, so this is again 3. So what will be the value of V3 will be equal to 2.18 multiplied by 10 raised to the power 8 multiplied by We have Z by N, you can see Z by N. So that will be 3 divided by 3 cancel out. That will be only 2.18 multiplied by 10 raised to the power 8 centimeter per second. I hope this part is clear. Very simple question. This is the basic question I can say. Okay. Now next part is associated with the energy of the electron which is present in a specific orbit. So first part is we know that total energy will be equal to the summation of kinetic energy as well as potential energy. Potential energy we already know that will be equal to minus k q1 q2 upon r. If I talk about the any type of nucleus having charge Ze, electron's charge is E, so we can say that will be minus k Ze square over r. So that is the first part which is the potential energy. So that is the potential energy. I hope this part is clear. I hope this part is clear. Now the next portion in this case, you know the kinetic energy is half mv square. Kinetic energy half mv square. We can say that mv square over r will be equal to Ze square over r square. That part we have already discussed. We are balancing the centrifugal force with the potential energy. So balancing with electrostatic force of attraction. Okay, I can make the diagram again. So that will look like this. Okay. In center point, this is your nucleus. This is your electron. The distance is basically r. This having charge is Ze. Charge of the electron is E only. Distance of separation is r. So first part is the force of attraction and this part is the centrifugal force. So we are balancing this entire part. So from that part I can say mv square will be equal to our kZe square over r. If I am multiplying it with the entire part of half, I can say that will be half of the value of kZe square over r, kZe square over r. So that is the basic part related to the entire portion. Now from that particular part, I can say the total energy will be half mv square plus potential energy. This value comes out as the kZe square over 2r minus kZe square over r. So if you solve this entire part, that will be total energy will be minus kZe square over 2r. Now you can see from this particular part that total energy is basically negative of the kinetic energy. This is the negative of the kinetic energy. And if I am using the potential energy part, if I am considering potential energy part, that will be twice of the total energy. You can simply look at the values. Because potential energy is this much. If I am multiplying the entire part with 2, so the total energy is basically like this. If I am multiplying the entire part with 2, I will get this particular value, which is the potential energy. So I can say potential energy is twice of total energy, and total energy is the negative of kinetic energy by this simple equation. I guess k is missing in this particular case. kZe square over r square. So from this particular part, you can say that mv square is equal to, and half mv square will be equal to half of kZe square over r. Now this is the only requirement, and this is the final value. We know each and every value, and that's how you can solve the entire part. Okay. But if you are putting the value of r in this case, you can actually calculate the total energy value, you can calculate the potential energy value, you can calculate the value of kinetic energy also. Okay, so r is equal to 4 pi n square h square upon 4 pi square m k Ze square. You can put the entire value, you can take all the constant on one side, and then you can put the values here. So first part in kilojoule per mole, I can say that will be 1312 minus 1312 multiplied by Z square upon n square. So you can say that total energy will be equal to some specific constant term multiplied by Z square upon n square, that is in the negative term. If you are converting that particular part into kilocalorie per mole, then you can get another value. In case of electron volt per atom, you can say that will be minus 13.6 multiplied by z square upon n square. So for hydrogen atom which is present in the first orbit, you can say that value will be E1 is equal to minus 13.6, and that's how you can actually calculate each and every value. So let's say this is your ground state. Okay, this is your second state, this is your third state, this is your fourth, this is your fifth, this is your sixth. Okay, and that's how you can draw different values. Now if I talk about this E1 value, that will be minus 13.6 electron volt per atom. If I talk about the E2 value, I can put the values here, and will be 2 in this case. It means minus 13.6 divided by 4, that will be 13.6 divided by 4. So I can say 4 3s are 12, that will be 1, 3.4. So that will be minus 3.4 electron volt per atom. If I talk about the value of E3, again you can solve this particular part as 13.6 divided by 9, 3 square 9. So that will be 9 ones are 9, 1 2 3 4, approximately 1.51, minus 1.51 electron volt per atom. So you can see the value is actually increasing. The value is increasing. Least negative term is having the minimum value. So this is your ground state. So this is your ground state. This is your excited state, which will be the first excited state. This is the second excited state, and so on. So you can calculate each and every value for hydrogen atom. I hope this entire part is clear, and you can see initially the gap is more. In second case, gap is decreasing. In third case, it is going to decrease further, and that's why I told you that these are not equally spaced. The space between them is going to decrease when you are increasing the value of n. I hope now the entire portion of a Bohrs atomic model is clear to everyone. We discussed about each and every part related to the energy, related to the velocity, related to the radius of the orbit. Now for hydrogen atom, you can say that value is already been calculated. We have already calculated the entire value, and you can put the values. But otherwise for hydrogen like a species, you know the formula, and that's why I told you that kinetic energy will be negative of the total energy, and potential energy is the twice of kinetic energy. This relation we have already established. Okay, I hope this entire part is clear to everyone. Now calculate the energy of third Bohr orbit of He positive ion. This is your homework. Very simple question. Very simple question. If you want to practice some more questions for basic part, to clear your basics, you can refer to NCERT. Again in this lecture I am talking about the NCERT only, because first of all you have to strong your basics. So just practice all those questions which are present in NCERT and whatever I have given you. In next class definitely we are going to discuss more advanced version of the questions. Okay. Now next part is, if energy of a fourth Bohr orbit is Li2 positive ion is X, then calculate the energy of sixth excited state of helium positive ion in terms of X. Now this question is a good question, I can say. This is a good question, because we know that En will be equal to E naught, something specific value, minus multiplied by Z square by N square. This part we already know. Now we have first part, which is lithium 2 positive ion. In this case Z value is a 3 and N value is fourth Bohr orbit. This is the fourth Bohr orbit. It means N is equal to 4 we are talking about. Okay, first part is done. Second part, we have He positive ion. And in case of He positive ion, the Z value is definitely 2. But in this case, N value is sixth excited state. I told you earlier. I told you earlier, just look at the diagram. This is the first excited state, means in this case, if the n is actually 1, first excited state means n is equal to 2. Second excited state means n is equal to 3. In the same way, if I am solving this question, sixth excited state means n is equal to 7. This is the only thing which you have to consider. Now, if I am talking about the energy for lithium 2 positive and in its fourth orbit will be equal to x, and that will be equal to minus E naught multiplied by z square, which is 9, divided by n square, which is 16. Okay, this value is already given. This is the equation number 1. Now, energy of He positive ion and in its seventh state, because it's the sixth excited state, that will be equal to again some specific value minus E naught multiplied by z square is 4, n square is 49. 7 sevens are 49. So this is the equation number 2. So I am doing equation number 2 divided by equation number 1. If you are dividing these two parts, you can say that we have energy of He positive in its seventh orbit divided by x, because this value is already given as x. So x will be equal to, that will be minus E naught multiplied by 4 by 49 multiplied by 16 upon 9 multiplied by minus E naught. Okay, this minus E naught cancel out. We have what we have? We have 64 divided by, that will be 9 nines 81, 36, 46, 44, 441. Okay, that value will be 64 by 441. So from that particular part, we can say that energy of He positive of seventh orbit will be equal to 64 by 441 x. Okay, so this is the only part you have to consider. I hope this entire portion is clear to everyone. Very simple analysis, very simple question, but you need to make sure that we are talking about the sixth excited state having n value is equal to 7. Okay, now first of all, the Bohr model was able to explain about the stability of atom, because now the electrons are revolving in a specific stationary path. So we can say from that particular part that this problem was solved, that there is no question on the stability of the atom. Now Bohr theory could give numerical expressions for the radius of the orbit, velocity of the electron, as well as energy of the electron present inside the orbit. It means we have the entire quantitative explanation about the atom. Okay, that part is also clear. And again, Bohr's theory explained the spectrum lines of hydrogen atom and hydrogen like species, because there is some absorption of energy by which you can see certain lines, and there is emission of energy in terms of their wavelength. So you can again see absorption as well as emission spectrum very easily. Definitely in the next class, I'll try to explain you better about hydrogen absorption spectrum as well as emission spectrum. That part we are going to discuss in the next class. But now we know that energy gap is present. Electron can move from one orbit to another orbit by absorbing the energy. Again, you can see the spectrum, and it's going to release the energy. Again, you can see the spectrum. In next class, we are going to discuss more elaborately what is Lyman series, Bohrs series. All these series we are going to discuss in the next class. Okay, so don't worry. But again, there were some drawbacks related to this particular part, and the drawbacks are very, very, very crucial. The first thing is, Bohr theory is only valid for single electron species, because when you are applying the entire part for multi-electron species, which is the realistic way, that theory was unable to explain the entire part. Bohr theory could not explain why the angular momentum of electron is actually equals to nh over 2 pi. It means it talks about the quantization of angular momentum, but why the angular momentum is quantized? We just had the postulate that it is going to be quantized, but why? Bohr also didn't know the reason. So that was the limitation related to the Bohr's atomic model. And one more thing which is very, very important, whenever you are applying electric field as well as magnetic field, Whatever spectral lines you are getting, these spectral lines actually split into another lines, and this phenomena was unknown at that time. So basically Bohr's theory could not explain the splitting of spectral lines in presence of magnetic as well as electric field. So there are two effects. First one is Stark effect, and next one is Zeeman effect. So that corresponds to the splitting of spectral lines into different other lines in presence of electric as well as magnetic field. So if I talk about this particular part, I can say that Zeeman effect is nothing but the spectral lines splitting in presence of magnetic field. So whenever we are applying magnetic field, you can see the splitting of spectral lines. So this reason was unknown because Bohr only talks about the orbit part, but orbit is like, you can consider like whenever you ask me my address, I can say that I live in a particular city. Let's say I live in any of the city you can consider. Okay, let's say I live in Pune. So Pune is having a large area. So many small portions are there, but you cannot find the exact location. So that was the reason, because the Bohr only talks about a large space where you can find the electrons. So orbit is like that city, but you cannot locate exactly electrons. To locate the electrons, you need to know like in which particular area I am residing and in which society I am actually living, so that you can exactly locate my actual location. So this was missing. So that's why whenever you are applying magnetic field, you will go deep into the area part. So from city you can go to the area part, in which area I am residing. And again, when you are applying the electric field, again you will get the idea of in which particular society I am living, so that you can get the actual location. That's why you can see the splitting of these spectral lines. So the first part is splitting of spectral lines in presence of magnetic field is basically your Zeeman effect. In the same way, the splitting of spectral lines in the presence of electric field is actually known as your Stark effect, and that was missing in the entire part. So this is the entire portion related to your Bohr's model as well as its drawback. So definitely in the next class, which is going to be very important as well as very crucial, because in that class we are going to discuss about the idea of spectral lines, as well as we are going to start the next portion. Although this model was also unable to explain the Heisenberg's uncertainty principle, as well as this particular part was unable to explain de Broglie's hypothesis. So that part also we are going to cover in the next session. Okay, so I hope this entire part is clear. Although this entire portion, this entire lecture was more of a theoretical lecture to understand, to give you the basic understanding about the structure of atom, but you can practice some basic questions by yourself. And in next class I'll try to make sure that we will have enough ample amount of questions, so that we can discuss various aspects with the help of questions also. Okay, so don't worry. Okay, and I hope everyone enjoyed this particular session. That's all from my side. Thank you so much.